this is not started. Now it's started. Now we can begin. Good afternoon, everybody.
Good afternoon.
Thank you. That's what I like to hear. All right, somebody's excited. And it's exciting week, really. This is the final section. I don't think you guys quite processed that. This is it. We get volume here, and we're done with the chapter. So we got our assessment next week, and then we move on to funny, cool the project after. And then between assessment and project, we've got the interesting subjects, the weird stuff of geometry. So before there, let's talk about our topic today. Right? Volume, right? Three-dimensional space. This is possibly the most important piece of geometry, certainly the most real-life applicable, because everything we actually interact with is three-dimensional. We live in a 3D world. Even when you're measuring two-dimensional stuff, even when you're finding area, you think you're finding area, but really, it's a volume, right? You did the area of the room. How much carpet do you need? It's sold in square feet, yes. But carpet has a thickness to it, right? You can get the real thin carpet like we have here, or you can get the nice soft, cushy, fluffy stuff, right? It takes thickness. And when you're installing, say, like a baseboard or something, or on the edge of the wall, that has to go on top of the floor. So you have to account for the thickness of your carpet now. Everything has three dimensions to it that all need to be considered in one fashion or another. So volume here is going to be huge, and we're going to get to answer some really cool questions, like dealing with the Great Pyramids. Okay, we can find the actual amount of stone used in those. That's pretty cool. I think on problem set 2, I've got one from the St. Louis Arch, right? The Gateway Arch in St. Louis. Very cool thing to check out. Totally recommend visiting there. Been there myself, been up inside it. It's neat. So let's practice a couple examples together today, and then I will turn you guys onto the problem set. And I think, since we got enough of you here, I think I'll have you pair off and work together on the problem set. Okay? So let's get through these as quick as we can together, so you have as much work time as possible. That means notebooks out, everybody. Follow along. Write this down. And I'm going to be relying on you guys for the calculations. So have your calculators at the ready to actually multiply what needs multiplied. That's running. Okay, we're going to start off with a fairly simple one. We've got this shape here, whatever it is. Step 1 is always figure out what shape are you dealing with? What type of shape? Because we've got a lot of formulas for volume. Honestly, it's not too terrible of a process. Figure out what shape you need, find the appropriate formula, and substitute in the correct measurements into said formula. Right? That's the basics of it. But we've got to figure out which one this is. So this is going to test your visual spatial reasoning skills. I need you to be able to look at this picture, this two-dimensional drawing, and interpret it as a three-dimensional figure. Okay? So what we are supposed to have here is a trapezoidal prism. That is to say, we've got one base down here that is a trapezoid. Okay? And one identical base up here that is another trapezoid. And we have to imagine that those are the bottom and the top of this prism, and they are parallel to each other. And we have a great big rectangle here. Well, that is the front, that's facing us. And then this skinny rectangle is the back, right? That's farther away. So we've got a big one up front and a little one skinny behind it. Can everyone see that? Or a better question, does anybody not see that? I'm struggling to interpret this picture. Okay. Make sure, because if you're struggling on that step, the rest of it's not going to make any sense. Right? Got to be able to interpret the picture first. Okay, so knowing that, recognizing this as a trapezoidal prism, we're going to use the volume formula for a prism, which is take the area of the base and multiply by the height. And the height is the distance between those two congruent bases. We could tick this thing up and turn it sideways, and we would still call this 10 centimeters the height. Okay? It's the height between bases. Now, our base of our prism is itself a trapezoid, so we need to find the area of a trapezoid. What's the formula for area of a trapezoid?
Something like B1 and B2.
Uh-huh. B1 plus B2. Anybody else want to help me out? What else was there? Yeah, check your notes. You have all these formulas written down somewhere, don't you? This is probably also in the back of your planner, if you've got that.
1/2 height minus base 1 plus base 2.
Yeah, there you go. So you gave it to us as 1/2 times height times base 1 plus base 2, right? Like that?
Yes.
I prefer it base 1 plus base 2 divided by 2 and group those together, because this reminds me where the formula comes from. It's the average of the bases. That's just a little shortcut conceptually for me. Instead of trying to remember it as a list of these items in order, I remember, average of the bases times height. And then I know to add them up and divide by 2. That's how I find the average of things. So for me, this is more convenient. If you like 1/2 times h times b1 plus b2, go for it. I don't care how you write it. Right? Multiplication is commutative that way. You can rearrange it. Okay, so we need to get these measurements from our trapezoid there. What is our height? Height of the trapezoid. Now, I know, it's confusing, right? There's like 2 different h's. We almost ought to call that one capital H. Maybe that would be better. Right? Lowercase h, the height of the trapezoid. 4 centimeters. Very good. And the 2 bases of the trapezoid. I can see one of them right there is 8 centimeters. Right next to, notice we got the right angle bracket there telling us, yes, this is in fact perpendicular to that base, so that's a perfectly good height. So we know one of them is 8. Where's the other one? It's 2. It's way up here. Right? They didn't give us all the measurements around this trapezoid. But remember, the bases of the prism are congruent. So I can transfer all these measurements down to here. So if this is 2 up here, this must be 2 here as well. So it's 8 plus 2. Eight plus 2 makes, everybody? 10 divided by 2 is?
5.
5 times 4 is?
20.
So the area of the trapezoid is?
20.
20 centimeters squared. We're almost done. Now we've got that. I called it A, but it's the area of my base, so it's really our capital B there. So to find the volume of the whole thing, we'll take our 20 centimeters squared and multiply by 10 centimeters. Very good. Oh, that's an easy one. 20 times 10 gives us
2,200.
200 centimeters
Wait.
volume cubed.
So why are we using a square like that?
Because that was the area.
Because this was an area of the base. Yep. I think it was one of the other books that we used when I introduced volume as a stack of papers. Right? We found area. We started with, hey, how big is this sheet of paper? Okay? That's area. It's a two-dimensional measurement. Okay? We measured length times width, or base times height, whatever. Key being those were two perpendicular measurements. That was the important bit. And that gave us the size of a sheet of paper. And then we start stacking more and more identical sheets of paper on top of each other. Right? And I said, hey, how tall of a stack do you want it? I want to go 10 centimeters tall. That's a lot of sheets of paper. Now how much space is this whole stack taking up? Right? And you can break down, not every formula breaks down to this. Right? The pyramids and the cones have that extra 1/3 because the papers keep changing sizes. But the idea is there. You could divide it into layers, right? And do each layer and add up all the layers. We're adding up all those sheets of paper. And it's important to remember that this height must also be perpendicular to the base plane. So that base piece of paper, you have to measure, no, don't measure like this. You got to measure perpendicular to that. Because we're measuring a three-dimensional object. Our three dimensions, x, y, z, are perpendicular to each other. So the measurements must still be always perpendicular to each other. Okay? If you encounter something like, you've got a little rectangular, no, that doesn't give off the right picture. It looks like it's just sideways. Let's see here. Like a cylinder. Like this slanty kind of guy. All right? It's a cylinder, but it's crooked. These two are still parallel to each other, but the height is not this length along the cylinder. The height would be, right, down there, perpendicular to that plane. Right? Just like we did with triangles. And sometimes you don't have a non-right triangle. You got to find the perpendicular height. You still got to find the perpendicular height now in 3 dimensions. Okay? This requires a little bit more visualization. Okay. Any questions then on volume of basic shapes? So I could give you any one of those from, where was the table here? They gave us that summary at the end. That was really convenient. Yeah, this guy. And I said in the video, definitely have this in your notes. In fact, you should like star the page that it's on, put it in the corner of your notebook so you can flip through real fast and find it. Be like, ooh, there's the table. All the formulas right there. So I could give you any one of these, and you guys could find the measurements, put it into the formula, give me the volume, right? Let me know any hesitancy now. We'll dive deep if we need to. Let me know. No, we're good? Those are all okay? Okay. So the challenge will be, given a context, right? The problem with a given problem, as it were, is understanding what are they talking about? What is the shape? This is why strategy, first strategy is almost always drawing a picture. Because you got to figure out what shape they're dealing with. Reading through and interpreting. Okay, they're describing this thing. They didn't explicitly say the base is, but they're describing it as a square or a pentagon or something, right? Infer that. Apply the appropriate measurements. Now, no, not there, this side. The other challenge you might face with these problems is with units. Right? So we're going to practice a little unit conversion here. I have a can of juice. All right? Here are the dimensions. But I really want to know how many cups of juice is that actually? Because when I put together my breakfast in the morning, I don't pour myself a nice, tall, cubic centimeter of juice. Right? Does anybody drink their juice in cubic centimeters? No, you drink it out of a cup, right? which if you use the small ones, they are actually usually pretty close to an actual fluid ounce cup, 8 ounces. Maybe you get the big tall cup and it's a 16-ounce cup. You get the big tumblers, right? But point is, like, how many actual cups, right? Give me a practical unit, okay? Engines are measured in cubic centimeter. Juice is not. So I want to find the volume of this can, how much juice is it holding, and convert into cups. Give me something practical. And then I can figure out from there, okay, if I have a cup per day, this can will last me how many days, and I know how many I need to get from the grocery store, right? Will this last me the week? Will it last me a month? How much juice is that? So, step 1, what shape are we dealing with?
Cylinder.
A cylinder, he's very sure. What clued you in? What clued you into cylinder?
Can.
It's a can. Most cans are cylindrical in shape, right? We can also get that they gave us a radius and a height. That's a good sense that we're dealing with at least cylinder or cone, right? Yeah, so it's a cylinder. So a quick sketch here of a cylinder, just so we get an idea. And it's definitely taller than it is wide. Okay, so it's not like a tuna can shape. And we have our radius here, R, and our height, H. So we want to find the volume of a cylinder, which is, what's the formula for that one?
That's a long one. That's squared plus B. Also, that's correct.
S2A.
The cylinder. Oh, we're looking for.
Give us the final simplified version. Yeah, volume, not surface area.
Oh, yeah, I am looking
I thought so, because you mentioned plus. I'm like, it sounds like surface. Yeah, pi r squared, which remember, that's the area of a circle, times our height, h. Because it's a circular base, and we want to stack those circles h high. So we're going to have pi times our radius here is 5.3. Square that and multiply by 17.7. Go ahead and do that now. Give it to me in terms of pi first. So just do 5.3 squared times 17.7. And let's go, they went to 1 decimal place so far, so give it to me in 2 decimal places. Okay, I want to carry my estimate an extra space. So we're going with 1, so our final answer will be to the 1 decimal place, so let's keep it 2 decimal places until we get to the final result. 19, fine. Can anyone confirm that? What, 497? Anybody confirm that number? We get a second? I've got a thumbs up back there. Okay, that's 1. All right, and units on that will be centimeters cubed. Okay, so there's our best, most accurate. Let's go ahead and multiply by the pi there. Because my cups at home are not marked in multiples of pi in there, so keeping it in this exact form will not help me get towards my goal of how many cups. If you tell me it's 2 pi cups, that's useless, right? 561.97 centimeters cubed. All right, do we have a second on that? Yep, nodding head, okay. Now comes the fun part. Now we've got to convert from cubic centimeters into cups. Well, I've given you a couple unit conversions up here, none of which are cups to cubic centimeters or vice versa. You could ask Google. Google does a great job of offering you just the instant. They do all the middle computations, go straight. Here's from cups to cubic centimeters. Okay? So practically speaking, you could just use that. Well, what if you don't actually have access to it? Let's go through the old-fashioned way, just a little bit. Again, you don't have to do this every time, but on a test you won't have access to Google. So let's practice making use of it. The standard conversions. These are often given. Right? You'll find these in some table somewhere on the back of your planner, or given in a test, or written on your calculator or cookbook or something. Right? They'll give you some conversions, but not every possible combination. So, unit conversion. Everything becomes a fraction. Put all this over 1. And we're always multiplying by fractions. The unit conversions, these equivalencies, become a fraction. They are a ratio. It says, hey, every ounce is equivalent to 29.57 milliliters. So if I wrote 1 divided by the other, because of those, yes, they are different numbers, but they're also different units, that is technically something divided by itself. It's just 1. I'm multiplying by a fancy form of 1 every time here. We're going to start by getting rid of the unit that we've got. So we've got cubic centimeters. I want to convert that I can convert it to milliliters. Okay, simple enough. Make another fraction. I have centimeter cubed on top. I want to put centimeter cubed on the bottom so that they reduce. And then the other one goes up top, in this case milliliters. Now we fill in the numbers go with the unit. In this case, it's very simple. They're both 1s. Doesn't actually change. That's one of those metric definitional things. A cubic centimeter is a milliliter. Okay. Very handy metric. Good job. Now, notice what we did not do. Because we deal with fluids as human beings, we've dealt with fluids so long, we've decided, you know what, fluid volume needs its own unit. We're not going to keep carrying around this to the cube every time. Right? It gets excessive. If we were not doing that, if we wanted, say, cubic centimeters to cubic inches, okay, just go straight from metric to English, what would you have to do? If I had 5 centimeters cubed, right, for example, let's change the color here so it's not part of this problem, but for example, right? Well, we know the conversion for centimeter to inch, right? And that's 2.54 centimeters per inch. But that's only centimeter. I need centimeter cubed, right, to the 3rd power, which means technically you got to do this 3 times. Inch, centimeter, right? That way, centimeter and cube to 1, 2, 3 power. You guys see that? Why that's necessary? Right? If you wanted to go to another cubic of a linear measurement, right? Inch normally is 1 dimension. I want the 3-dimensional version, the cubic inch. Again, we've got cubic volume units. Milliliters does not need a 3rd power. We don't need to convert 3 times over. 1 and done. Cubic to just milliliter. Right? So we don't need to do this. Thank goodness. That'll save us a bit. But I point that out because you might need to do it on a different problem. Depends on what we're asking for, right? Okay, let's keep going. Back to here. I now have milliliters. I didn't want milliliters in the end. What can I convert milliliters to? Looking up here. I've got milliliters to ounces. Let's go milliliters to ounces. So once again, I have milliliters. Put that on the bottom. In fact, I need a slightly longer line. There we go. I want ounces. Put ounces on the top. I can cross out milliliters because it's on the top and the bottom. And put in the numbers. 1 goes with ounces. And 29.57 goes with milliliters. Almost there. I've gotten to ounces. We at least recognize that. I've seen that, written on bottles and cans and places. I'm gonna go all the way to cups. So finally we go, put ounces on the bottom, cups on top. 1 cup holds 8 ounces. Now I can cross out ounces. The only unit left is cups. That's the one I wanted. I am done with the setup. And now we just multiply across. You take the starting number, multiply by everything up here. Turns out they're all ones. We can skip ones because they don't change the number at all. And then divide by everything down here. Again, we can skip the ones. So we're going to take our 1,561.97, divide by 29.57, divide again by 8. Go ahead and do that now. 2.82?
divided by 29.
Okay. He got 6.6. First answer is not necessarily right. Let's get some confirmation on that. You back him up? I've got a second. Okay. That doesn't mean stop. The rest of you should, if you're calculating it, keep going. Check to be sure. This is good practice. You don't want to, maybe you typed the button in wrong. Maybe they both typed the button in wrong. There was still only 2. Okay, 6.6 cups. Yeah. So if I have a glass of juice every morning, this will last me 6 days, about a week, right? I'll need to add this to my weekly grocery list. Or if I go every other week, right, make sure you grab 2 cans. And then you have to decide, on that 7th day, do you have a small glass of juice? Or on the 6th day, do you have an extra large glass of juice, right? That's up to you. What do you do with the extra? Okay, any questions on 3-dimensional unit conversion? Okay, we've got 2 problem sets this week. So as I've done before, most of this one is going to be basic shape practice. Here's the thing, find the volume. And we get our one nice application there with the Great Pyramids. Unless you go up into level 2s, there's a little bit more abstract, but it's still fairly straightforward, guys. And the level 3 one, this one is extra tricky because finding the actual height of this pyramid might be a challenge. So if you want to challenge yourself in 3-dimensional thinking, try that one. And then we'll have more application questions on Wednesday's problem set, okay? So we got 1, 2, 3, 4, 5, 6, 7, 8. Perfect, there's an even number of you. Pair up and start tackling. I'll be around to answer questions.